In this lesson, we'll talk about exponential functions and their applications. What is an exponential function? Well, any function of the type b to the x, where b is the base and this base must be positive. Also, the base should not be equal to 1. That would be a very degenerated case. 1 to anything would be 1, so we would end up with a constant function rather than exponential. So that's why we assume that b is different than 1. However, b should also be positive. The condition for b to be positive is because we don't want to have a trouble when we take a negative number to some exponents. Since negative number raised to some exponents are not defined, for example, a negative number to 1/2, it won't be defined. So that's why we want to restrict the base to just positive numbers. How the graph of exponential function looks like? Well, if we try to see the graph of 2 to the x, let's develop a table of values. If x is, for example, 0, then 2 to the x is easy to calculate. 2 to the 0 is always 1. If x is 1, 2 to the x would be 2. If x is 2, 2 to the x would be 4. And so on and so on. We also could check some negative numbers. If x is -1, 2 to the -1 is 1/2. -2, it gives us 1/4. And we can plot those points. So -2, 1/4, -1, 1/2, 0, 1, that's a number 1. At 1, we have 2. At 2, 4, and so on. So we can check some points, and they will give us this pattern of increasing values. But if we want to check more points, for example, an irrational number, we can just approximate. If our x would be 3/2, then using calculator, 2 to the 3/2 would be approximately 2.8. And we can plot some more points. So 3/2 about here, 2.8, or maybe about here. We can check more points. It happens that if we use all real numbers as a domain, then all those points will be actually joined, and we end up with a nice and continuous curve like this, where to the left this curve is trying to approach 0 level, and to the right this curve is running away towards infinity. Let's recall some exponential properties. If you take a base to the negative exponent, you can perform this negative by changing the level. So that's the same as 1 over a to the n. Also, if you raise any base a to the fractional exponent, the denominator is a hidden radical. That really means the same as the nth degree radical of a, and then it can be raised to m. Either this way or that way. A to the m could be under the radical or outside of the radical. Let's practice on these two examples. 2 to the 5/2 is the same as square root. The square root is hidden in the denominator, and underneath you have 2 to the 5. Now we can simplify this because this invisible index 2 goes into 5 twice, so I can take 2 to the 2 out, and the other 2 is left over under the root. So it's the same as 4 root 2. Here, if we raise the base to the negative exponent, it's enough to take reciprocal of the base to the positive exponent. So that's really the same as 4. Let's graph more exponential functions and observe the graph and the base that is used for the exponential function. So the first one, 2 to the x, we already graphed on the previous slide. Let's repeat those numbers. So at 0, it's always 1. So no matter what is the base, the graph of any function of the type b to the x will go through the point 0, 1. Now I'm going to graph in blue the first function f. So if x is 1, the value is 2. So it's good to notice that at 1 we have exactly the value of the base, because anything to 1 is the same anything. So that's your 2. At 2, it will be 4. At 3, it will become 8. At negative 1, 1/2, 1/4, and closer to 0. So the graph looks somehow like this and grows very fast up. Okay, so that's 2 to the x. Now in green, let's graph 3 to the x. So again, 3 to the 0 is 1, so the graph goes still through the point 0, 1. And 3 to the 1 is 3, so the graph goes through 3. Therefore, it looks like it will be steeper here. However, 3 to negative 1 is 1/3, not 1/2, but 1/3. So the graph will be a little bit below the blue line. Okay, and maybe one more point to check. 3 to the 2 is 9. So it will go here. Let's try to graph it. It's a little bit below, but it has to fit between the x-axis and the blue line. So here we have a graph of 3 to the x. And the last graph, 1/2 to the x, let's do it in purple. This time, again, if x is 0, 1/2 to the 0 is still 1. But if x is negative 1, 1/2 to negative 1 becomes 2. So, looks like it's decreasing. And at 1 becomes 1/2, and at 2, 1/4. And at negative 2, 4. At negative 3, it would be 8. So the graph goes backwards, it's decreasing, it goes somehow like this. Still, the graph is approaching x-axis, so that will be the asymptote for the exponential graph. The purple graph represents 1/2 to the x. Let's look at properties of exponential function of the form b to the x. First of all, what's the domain? Well, domain, as we see, there's no restriction here. We could choose any x, so domain is all real numbers, not a problem. With range, though, all the values are really positive. We never had anything negative, right? So the range is from 0, but without 0, to infinity. We'll never get 0 when you raise some number to any exponent. It will always be positive. Next, if the base is bigger than 1, for example, function f and g, the blue and green, the base is bigger than 1, the function is increasing. So we have increasing function. What does it mean? It means that if n is smaller than m, then b to the n is smaller than b to the m. If I choose 2 points on the number line, let's say here and there, n and m in the increasing order, then the values of those functions will be increasing as well. This one is higher than that one. However, if the base is between 0 and 1, remember the base can't be 1 and it has to be bigger than 0. So if the base is a fractional number like that, for example, function h, the function is decreasing, which means that if I choose 2 points n and m anywhere in the domain, then the value of the exponential function b to the n will be higher than the value of b to the m. Another property that we already observed is that the y-intercept of any exponential function of this form, b to the x, is 0, 1. This is a common point to any exponential function. We also have no x-intercepts. The graph never crosses the x-axis. And the graph passes through the point 1b, because if we plug it in 1 for x, what we get is exactly the base b. So whichever the base was. Here it was 2 or 3 or 1/2. The next important property of exponential function is that this is a one-to-one function, which means it will have an inverse. But again, let's recall what's one-to-one function. That means that if the values of the function are equal, then the inputs are equal as well. This is actually if and only if statements. That means if the inputs are equal, then obviously the values are equal as well. Another important feature of exponential function is that any exponential function has a horizontal asymptote y equals 0. the x-axis is its horizontal asymptote. So now we have a couple examples of how to graph exponential functions by using transformations of the basic graph, in this case 2 to the x. We want to produce function g of x negative 2 to the x minus 3 plus 1. So what kind of operations do we need to perform, starting with the function 2 to the x and trying to get closer to the function g? So, from 2 to the x, I need to move the x by subtracting 3. So the first step would be to obtain 2 to the x minus 3, and that can be achieved by transforming the original graph 3 steps to the right. Remember opposite sign that you see by the x? So 3 steps to the right means the vector 3, 0. Then, to get closer to our function g, we want negative 2 to the x minus 3. To obtain the negative in front, we use symmetry in x-axis. We just flip the graph over the x-axis. And finally, g of x is the same as the previous function plus 1, which means we need to use translation by the vector 0, 1. One step up. Okay, so let's start with the graph of 2 to the x that was coming through the point 1 and 1, 2. The graph looks somehow like this. So that was in blue. Now, dark blue, we are translating this graph by vector 3, 0, so every point will be moved 3 steps forward. So this point becomes here, that one there, and the asymptote is still at the same place. So the graph will look somehow like this. The following graph in green, we are flipping the dark blue graph over the x-axis. So this point becomes here, that one over there, and the asymptote is still x-axis. So the graph will look somehow like this. And the last function, the g, the one that we're interested in purple, we are going to add 1. That means that our regular asymptote that was at x-axis, now it will travel 1 step up. It will be positioned here at 1. And every important point will be moved 1 step up. So this one here, this one there, and that one here. And we volunteer a graph. The shape of the function will look somehow like this. So the purple one is the graph of g of x. And next example. Again, let's list the transformation first, starting with 2 to the x. The first step would be to add 1, so 2 to the x plus 1. And we record what kind of transformation needs to be applied. So translation by the vector negative 1, 0, opposite sign to the number that you see by the x. Now we multiply by 1/2, so it's 1/2 times 2 to the x plus 1. In order to do that, we have dilation. We multiply the function outside, so it's dilation in y-axis, by the same factor 1/2. And finally, we subtract the 3. So h of x is 1/2 times 2 to the x plus 1 minus 3. So now we apply translation by the vector 0, negative 3. 3 steps down. And again, let's start with the light blue. That's our standard 2 to the x. Comes through these points. Then dark blue. Move it 1 step to the left, so this point becomes here, and that one there, and this one here. The asymptote is still the same. Then the green, we're going to multiply every y value by 1/2. So instead of 2, I will have 1. Instead of 4, I will have 2. Instead of 1, I will have 1/2. Oh, that looks like its original function. Original 2 to the x, back to the same. And this is not a surprise, because if we actually collect the powers of 2, then dividing by 2 is like subtracting 1. So this would really mean the same as 2 to the x. So we come back actually to the same graph. And finally subtract 3, which means that the asymptote that normally was at x-axis, now it becomes at -3. And we're going to graph this in purple as before. So every single point goes straight down. This one here, this one there, this one here, and volunteer shape. So that will be the graph of h of x. And one more example. As before, let's start with 2 to the x. Then we want to graph 2 to the -x. Here we need to apply symmetry in y-axis. Since x changes from positive to negative and otherwise, we flip over the y-axis. Now gain the negative in front, so it's symmetry in x-axis. And finally p of x, which is -2 to the -x plus 2. So we have translation by the vector 0, 2. 2 steps up. Okay, let's start with our favorite 2 to the x. Comes through those points. Now dark blue, symmetry in y-axis. So this point becomes here, that one over there. The 0, 1 is still in the same place, and volunteer shape like this. And the following step in green, symmetry in x-axis. Oh, that this point is flipped here, that one over there, and the 4 here. And graph it. And the final graph in purple. What's happened now? We are adding 2, which means our asymptote moves 2 steps up. This point becomes here, that one over there, here, and the asymptote is at 2. So the graph looks somehow like this. Let's graph the asymptote at 2. Okay, so the purple graph is our p of x function. Exponential function is actually very popular, is used in many application problems, especially the ones that involve growth or decay. So what kind of bases are the most commonly used? Well, 2 to the x is used quite often, but aside of 2 to the x, maybe 3 to the x, other bases are not as popular as something that is called e. A constant e is an irrational number, and it's approximately equal to 2.718. Since, as you see, this number is between 2 and 3, then the graph of e to the x is actually positioned between 2 to the x and 3 to the x. So it's higher than 2 but lower than 3. Obviously, this kind of indicator how steep is the graph you can find by looking at value at point 1. So the function 2 to the x has a value 2 at 1, 3 to the x has a value 3, but e to the x has a value 2.7 somewhere here. So it's in between. What is this number? Well, this number was chosen in such a way that a tangent to the curve e to the x at the point 0, 1, if you draw a tangent line, it happens that such tangent will have exactly 45 degrees with the x-axis, with the horizontal line. So for different reasons, this is very useful in calculus. That's why this constant e was chosen. It just simplifies calculations of various derivatives. Some other way of defining a constant e is by looking at the limiting value of the expression 1 plus 1 over n to the n. So when n goes to infinity, this expression is actually approaching number e. And you're welcome to check this on your calculator. You may want to plug it in this expression using x instead of n under y1. and then using table of values, observe what's going on with values of the expression when n is growing higher and higher towards infinity. I enter to the calculator the expression 1 plus 1 over x to the x, where x will represent our n. And then let's go to the table of values. Remember to set up table of values in the mode of ask for x, and then we can enter, for example, 1 if n is 1. The value of the expression is 2. If n is, let's say, 5, the value of the expression is 2.48. If n is 10, 2.59, maybe 100. Let's go with n towards infinity. Oh, it's already 2.7. Let's go into 1,000. We have 2.71. Already first two digits agree with the constant e. Well, let's try 10,000. Oh, even three digits. Try one more zero. 100,000. And as you see, our value is really approaching a constant e. If we want to see more digits, we can highlight this number and then see even more digits. Obviously, we can go even farther and check one with 6 zeros. As you see, the first four digits doesn't change. They already stabilize. But to see farther digits, we should highlight this number and then observe what's going on. So the first four digits are 7182. And if we enter another number a little bit higher for x, and the first four digits will be exactly the same, then we know that these four digits are already established. So let's try 1 and 1, 2, 3, 4, 5, 6, 7 zeros. The number really agree on the first four, even 5 digits. It's 718281. So we are sure up to 5 digits. Therefore, as we checked, yes, if x is approaching infinity, the value of our expression 1 plus 1 over x to the x is really approaching the constant e. So that's one way of defining number e. The other way, as I mentioned before, is such a base of exponential function e to the x that a tangent line at the point 0, 1 has a slope equal to 1. So this is 45 degrees, slope equals 1 of this tangent line. Now we have two application problems. Application in the sense that we are using exponential function, but we are combining them by applying various operations and producing some new type of functions. So let's graph these two new functions that involve e to the x by using graphing calculator, and we are going to observe the asymptotic behavior of these two functions. Okay, so the first function seems to be an even. It's quite easy to check that this is an even function. F of negative x would be e to the negative x plus e to the negative negative, so it's positive x, over 2, which is the same as the original f of x, because addition is commutative. I enter the f function to the calculator, which is e to the x plus e to the negative x over 2. Let's graph it. Let's see the graph in the window from negative 5 to 5 and negative 5 to 5. Well, we see it's very symmetrical. It is even. Let's graph it on the paper. Okay, so we observed that our graph was approximately like this. Very symmetrical. So asymptotic behavior, well, towards positive and towards negative infinity, both arms of this graph are going towards infinity. There's no asymptotes here. However, it is even. So f is even. Let's graph g function. I enter this under y6. 5 over bracket 1 plus e to the exponent, and you make sure that you put a bracket around this exponent negative 0.5x and then complete the two brackets. Graph it in our previous window. It looks like this. If we want to see a little bit more, let's zoom out. Number 3, enter. That looks like we have a nice horizontal asymptote at the level 5. You can also zoom fit, which is number 0. And we clearly see the shape. It has an asymptote at 0 and it has an asymptote at 5. It's very symmetrical. About this point 0 seems like 2.5. This kind of curve is called logistic curve. The second graph, when we graphed on a calculator, it looks somehow like this. Here we could observe two asymptotes, the x-axis, but also an asymptote at the level 5. So y equals 5, it's another asymptote. Y equals 0 and y equals 5. Okay, let's determine the domain of these two functions involving exponents. Well, the first one, we need to protect the denominator. We need to make sure that 1 minus e to the x is different than 0. So as long as this condition is satisfied, we'll have our domain. So if a point satisfies this condition, a point belongs to the domain. When this happens, let's move the e to the x to the other side. E to the x must be different than 1. Well, recall how e to the x looks like. E to the x looks like that when this point is 1. So it happens at 0. So this is equivalent to say that x equals 0. Therefore, our domain equals all real numbers but not 0. Second example, here we have a root, so we have to protect the radicand. Therefore, the condition to check is when 1 minus e to the 2x is bigger equal 0. Well, bring the e to the other side, and that happens when e to something is smaller equal 1, but e to the 2x is smaller equal 1 when the input, which in this case is 2x, is smaller than 0. So this is equivalent to say that 2x must be smaller equal 0, which means that x is smaller equal 0. And we're ready to claim the domain. The domain of f is equal from minus infinity up to 0, including. Now we have some application problem. The exponential function given by this expression gives the amount of medication in milligrams in a patient's bloodstream 2 minutes after the medication has been injected into the patient's bloodstream. So t is time and a of t is the amount of medication. Find the amount of medication to the nearest milligram in the patient's bloodstream after 45 minutes. T is in minutes. So we can just use the 45 instead of t and evaluate what a of 45 is. 200 times e to the negative 0.014 t, and t is 45. And this can be calculated by calculator, so this is approximately 106.5 milligrams. Please check on your own. When you try to enter this expression to the calculator, make sure that you use brackets for the exponent. So enter something like that, 200 times e to the exponent, this little dash, bracket, negative 0.014 times 45, bracket, and enter. Well, since the question really asks till the nearest milligram, we should round it to 107 milligrams. The next part of the question asks us to determine how long it will take to the nearest minute for the amount of medication in a patient's bloodstream to reach 50 milligrams. So now we have the answer, now we have the amount of medication given, so we're really looking for the solution to this equation. When a of t, for what kind of t, a of t, is actually equal 50. We could do it algebraically if we know logarithms, but at this time we can do it by using graphing calculator. So let's use it in order to find out when the amount of medication will diminish to 50 milligrams. Let's plug it in the formula for the amount of medication under y1 and the 50 milligrams as a constant function under y2. We need to figure out what kind of window to assume. Since time is positive, let's start with 0. Go maybe up to maybe 200. And with the y value, we'll start with 0 and go up to 200 as well. Graph it. So this is our diminishing amount of medication in the bloodstream, and that's our level 50. So we are interested in the coordinates of this intersect point. Go through the second calc, intersect, number 5, and first curve, yes, enter, second curve, yes, enter, and the guess is about here as well. And our intersection, the x-coordinate, which in our case is time, is approximately 99 minutes. So that's our answer. After 99 minutes, the amount of medication in the bloodstream will be around 50 milligrams. And our t turned out to be approximately 99 minutes, which is the same as about 1 hour and 39 minutes. Here's our last application problem. The number of baths in a lake is given by this formula, where t is the number of months that have passed since the lake was stocked with bass. How many bass were in the lake immediately after it was stocked? So that's a question of what was the population of bass at the time 0. Therefore, we really need to find out what t of 0 is, and that shouldn't be too difficult. So 3600 over 1 plus 7 e to the, instead of t we have 0, so e to the 0 is the same as 1, which really means 3600 over 8. And that becomes 450. So originally it was 450 fish. How many bass to the nearest one were in the lake 1 year after the lake was stocked? Well, since t is in months, 1 year is 12 months, so we really need to evaluate p of 12. Again, let's plug it in everything to the formula. 1 plus 7 e to the negative 0.05 times 12. And now if we use calculator, we should end up with approximately 744 fish. Again, make sure that you use enough brackets. For example, you must use a bracket around the denominator. You also must use a bracket around the exponent to make it work. After how many months we should expect to have 2000 bass in the lake? Well, this time we need to solve the equation when 2000 is equal to the population of t. T is in months, and we are solving for t. Find t. And this time, let's use graphing calculator. Plug it in the formula for p of t. So under y1, you will have your p of t expression, and under y2, you may want to use 2000 as a constant function. And after graphing both of these, you're finding the t-coordinate of the intercept point. So again, we need to enter the formula for the amount of bass, which is under y3. Remember to use enough brackets, especially around the exponent and around the whole denominator. And we're going to compare with the level 2000, so that will be our constant function 2000. Let's graph it. And yes, we have a logistic curve, and we are interested in this intersection when the amount of bass will be 2000. So second calc, that will be intersect. First curve, second curve, enter, and the guess, enter again. We end up with about 43 months. After 43 months, we'll expect to have 2000 bass. Since the next question asks us to observe what's going on with the amount of bass when we proceed towards infinity, maybe we can just change the window and extend the x to maybe 1000 and see what will happen with the graph. Yes, we see that this graph stabilizes. And what is the approximate value here? Let's trace. And as you see, the y value is 3600. So we know that in the long run, the graph is trying to approach 3600. The calculator gives us the rounded number, but it's never actually 3600, so it's always tiny bit less than that. However, we're talking about fish, so you can't talk about part of a fish. We round to the nearest one. That's why we have 3600. What will happen to the bass population as t increases without bound? So now, after looking at our graph, we observe that if t goes towards infinity, then the population of bass is trying to reach 3600 fish.